Okay, 5.5, solving rational inequalities. So rational inequalities, a statement that one rational expression is less than or greater than another rational expression. Okay, solving an inequality means finding all possible values of the variable that satisfy the inequality. So there's two ways of solving rational inequalities. Okay, so there's graphically and algebraically. When stating the solution, we state the intervals in which the domain satisfies the inequality. So just to review, we use either closed brackets or open brackets. So closed brackets are like square brackets. So that's if it includes. So see this underline in the inequalities, the greater than and less than symbols? This means greater than or equal to and less than or equal to. Okay. And then open brackets are going to be the round brackets, and we use these if the numbers are not included or when stating negative infinity or infinity, because we can never actually get to negative infinity. We can never actually get to infinity. Okay. So for example, greater than or less than without that underlined. Okay. And we do that at an asymptote as well. So here are some steps for solving inequalities graphically. So first we're going to find the x-intercepts. Okay, and this is possible changes from greater than to less than. Okay, then we're going to find the vertical asymptotes. Then we're going to use x-intercepts and the vertical asymptotes to create a chart. So the first row in the chart, we're going to divide into intervals starting at negative infinity and listing the vertical asymptotes and x-intercepts in numerical order. Okay, we've seen this before. And then we're going to finish with infinity. It's going to look a little bit different, but very similar to the vertical asymptote chart in where we use the equal sign instead of an inequality. Then in the first column, we're going to list each factor. Same as the vertical asymptote chart. Okay, we're going to choose numbers within each interval, and we're going to decide the sign of each factor, and then we're going to basically multiply the factors, multiply the signs and determine the overall sign. And then we're going to compare the overall sign to reference back to the actual starting question. So let's go through these steps, because when we do this in an actual question, it's going to make much more sense. So solving a rational inequality graphically. Okay, solve f of x equals x plus 1 over x squared minus 3x. Okay, so first I'm going to, I'm looking at the denominator and I can factor that. So let's factor this to x plus 1 over x minus 3. And that's greater than 0. Okay, so what is the x-intercept? We'll start with that. Well, it's when the denominator equals 0, so x equals negative 1. The vertical asymptotes is when the denominators will equal 0, so x equals 0 from the monomial and 3 from x minus 3. And let's solve for the horizontal asymptote, because this is rational, right? So it's going to be y equals, well, the degree in the denominator is 1 greater than the degree in the numerator, so you take the coefficients, which is 1 over 1. Okay. So, a little bit different, but same idea here. We don't have to test the vertical asymptotes on the left or the right. So we're going to start with negative infinity. And then we're going to include these numbers here. So negative 1 numerically comes first, then 0, then 3, and then we finish with infinity. And these three factors here from the original equation, we have to list them down the left side. So what's a little bit different with this chart is that we just simply pick a number between negative infinity and negative 1. So let's go negative 2. Let's pick a number between negative 1 and 0, negative 1/2. 0 and 3, I'm going to pick 1. 3 and infinity, I'm going to pick, 10. So Negative 2 plus 1 is negative. Negative 2 is negative. And negative 2 minus anything is negative. So that's negative. Minus a half plus 1 is going to pull us into the positives. Negative a half is actually negative. And negative a half minus 3 is negative. So that's positive. Okay. 1 plus 1 is positive. 1 is positive. 1 minus 3 is negative. So that's negative. And then I kind of do an extreme number just in case we have like plus or minus here. So 10 plus 1 is still positive, 10 is positive, and 10 minus 3 is positive. Right? If we put like a 4 or something here, we would have had to actually think a little bit, but putting like a little bit more of an extreme number gets us to like not think so much. It's great. Sorry, this was out of whack. Sorry. Okay. So our question, going back to the beginning, is when is this function greater than 0? So it's greater than 0 here and here. So we're looking at the intervals that are greater than 0. So I'm going to say that the solution would be, right, would be here. Negative 1 to 0 and 3 to infinity. And we would use open brackets because this is not underlined. Okay, so let's check with decimals. X plus 1 over x squared minus 3x. Okay, so what we're looking for is when this function is greater than 0. So it would start at 0 at negative 1, right? So we're looking at the 0 on the y-axis, but we're quoting the answer in the x's, right, in the domain. So negative 1 to 0, right, because 0 is the vertical asymptote. And then the other vertical asymptote, which looks like 3 maybe, so 3 to infinity. So negative 1 to 0, 3 to infinity. And if we want to just like quickly sketch this, we go through negative 1. I'm looking at the horizontal asymptote. Okay, so this looks like it goes through and then it comes back up. Okay, and then we have this one. And then we have, and then this is just like a rough sketch. And then we have this one here. Oh, my mistake. Horizontal asymptote is 0. Because we have a difference of like 1, exponent 1 in the numerator and then exponent 2 in the denominator. And then we have these x equals 0 and then x equals 3. Okay, example 2. Solve x over x plus 7 is less than or equal to negative x over x minus 2. So I'm going to go ahead and bring this over and I'm going to rewrite x over x plus 7 plus x over x minus 2. And then we're going to keep the inequality sign the same, is less than or equal to 0. Okay, I'm going to bracket these binomials. And I'm going to multiply the first one by x minus 2 over x minus 2 so that we get a common denominator. And I'm going to multiply the second one by x plus 7 over x plus 7 so we get a common denominator. Okay, so when I rewrite this, we're going to have the common denominator, and then we're going to have x bracket x minus 2 plus x bracket x plus 7. Okay, these numerators, we actually have to expand the whole things in order for us to collect like terms and then see if we can refactor. So I get x squared minus 2x plus x squared plus 7x all over x minus 2x plus 7. Okay, so we get 2x squared, and then negative 2 plus 7 is plus 5x, all over x minus 2, x plus 7. So I'm good like factoring out of the numerator an x, and I'm just going to leave the 2 and the 5 because it doesn't really make anything simpler. So now let's go through that algorithm, okay? So x-intercept, we're going to have when the numerator equals 0. So we have 0 and negative 5 over 2. Okay. We can do a y-intercept if we want. We don't have to. It's going to be 0, right? Because we have a 0 here. Okay. The vertical asymptote is going to be when the denominator equals 0, so x equals 2 and negative 7. And the horizontal asymptote, we have an x squared in the numerator and an x squared in the denominator, so it's the coefficient. So the coefficient, if we were to expand this, oh, well, it's here. It's 2 over 1. So y equals 2. So let's go ahead and set up our chart. Okay, and we need these two numbers and then these two numbers in there alongside a negative infinity and a positive infinity. So we're going to go negative infinity, negative 7, negative 5 over 2, 0 to infinity. And then down the side, we're going to put everything in this original. So we call this the original equation because we haven't canceled anything out. Okay, so we're going to go x, 2x plus 5, x minus 2, x plus 7. And then we're going to test numbers in each one of these intervals. So let's choose a number between negative infinity and negative 7. I'm just going to do negative 10. Let's do the column. This is negative, negative 20 plus 5, negative, this is plus, negative 10 minus anything is negative, negative 10 plus 7 is still negative. So this is positive. Now, a number between negative 7 and negative, this is like negative 2.5. Let's go negative 5. So negative 5 is negative. Negative 10 plus 5 is negative. Negative 5 minus anything is negative. Negative 5 plus 7 is going to be positive. So this is negative. Okay, number between negative 2.5 and 0, let's choose negative 1. Okay, this would be negative. Negative 2 plus 5 is positive. Negative, positive. Okay, between 0 and 2, it's going to be positive, positive, negative, positive. So that's negative. And between 2 and infinity, I'm going to do that big number 10. Positive, 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 and that is positive. So as a solution, we're looking for these numbers that are less than or equal to. We're looking specifically for this and this. So it's going to be this interval here and this interval here. So the solution would be box, like box brackets, negative 7 to negative 5 over 2, because this inequality sign has an underline. So we're going to use includes, and 0 to 2. And now let's actually check with Desmos. So this is the Desmos graph. I just put in the x over x plus 7 plus x over x minus 2. So we have like the asymptotes. Okay, this part of the graph is above, this part of the graph is above as well. And then if we zoom in, we can see that it's above between negative 2.5 and 0. Okay, so going here, we're going to put an x-intercept at 0 and negative 2.5. Okay, and we're going to put vertical asymptotes at 2 and negative 7. And this is just a quick sketch. So x equals 2, x equals negative 7. We're going to put a horizontal asymptote at 2. Okay, so the horizontal asymptote, y equals 2. So we know we're about right here, and we're here, and we are here. So the solution when our function is less than or equal to 0 would be this leg here and this leg here. So algebraically, to solve the rational inequality algebraically, what we do is we rearrange the inequality so that one side is 0, and then we combine the expressions on the non-zero side using a common denominator. So we kind of just did that anyways. And then what we want to do is performing any of the following operations on an inequality produces an equivalent inequality. Okay, so inequalities are treated just like equal signs except for one rule. So the adding and subtracting a quantity from both sides treated the same. Multiplier dividing a quantity, a positive quantity from both sides, same. The only thing that happens is that when you multiply or divide a negative quantity, then what you have to do is you have to reverse the direction of the inequality. Okay, then what we're going to do is make a table to examine the sign of each factor, and that's what we've been doing, and the sign of the entire expression on the intervals created by the zeros of the numerator and the denominator. So let's start. Okay, solve the rational inequality algebraically. So we have x minus 2, which is linear, and then we have 8 over x, which is a reciprocal function. Okay, when is this less than this? Okay, and obviously we put the x does not equal 0 because that's going to be the restriction in the denominator. So let's move over the 8 over x. So I get x minus 2 minus 8 over x is less than 0. Now we have to find a common denominator. So I'm going to multiply this one by x over x, the negative 2 by x over x, and then leave the negative 8 over x. So I get x squared minus 2x minus 8. This is all over x is less than 0. So cross multiplying that, I can get rid of the x. We're simply dealing with this quadratic. We want to know when this is less than 0. So because we have an x squared and an x term, we're going to go ahead and we're going to find two numbers that multiply to negative 8 and add to negative 2. So 1, 8, 2, 4. If we put the negative on the 4, that adds to negative 2. So x plus 2, x minus 4. Okay, so we get the zeros of x equals negative 2 and x equals 4. And because there's an x in the denominator, we have a vertical asymptote of x equals 0. I mean, we could have kept this going. That's fine. But we have two x-intercepts, and then we have like the vertical asymptote. Okay? And of course, coming back over here, full circle, x does not equal 0. That's because there's a vertical asymptote. So let's examine the sign. Okay, so negative infinity. We're going to go negative 2, 0, and then 4, and then infinity. Okay, and we're going to take all three of these terms, so x plus 2, x minus 4, and x, and we're going to put that in the left-hand side, and we are going to fill out our chart with our signs. All right, let's choose a number between negative infinity and negative 2. Let's go negative 10. This is negative, negative, negative. We get negative. Negative 2 to 0, let's go negative 1. Plus 2 is positive, negative, negative. Okay, so we get positive. 0 to 4 is 1. Positive, negative, positive. So we get negative. 4 to infinity, let's do 10, positive, 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 we get positive. Okay, so we're not checking decimals with this. We're not doing the x-intercept, or we did the x-intercepts. We're not doing like the y-intercept, the horizontal asymptote. We're not graphing it. We're just going to state the solution. So when is this less than 0? Well, here and here, so negative infinity to negative 2. And we're using round brackets because we're strictly less than, and 0 to 4. Example 4, use algebra and a sign chart to solve the rational inequality algebraically. So we're going to bring this term onto the left-hand side. We get 240 over t plus 8, right? And that's a binomial, minus 20t over t plus 1. And then that's going to be greater than 0. So when is this greater than 0? So we have to find a common denominator. I'm going to multiply by t plus 8 over t plus 8. And then I'm going to multiply by t plus 1 over t plus 1. So I get 240 t plus 1 minus 20t t plus 8 all over t plus 8. T plus 1 greater than 0. Okay. So now we're just going to expand everything in the numerator and collect like terms. Okay, so I get 240t plus 240 minus 20t squared minus 160t. Okay, same denominator. Leave the denominator, don't expand it. Okay, so I'm going to get negative 20t squared plus 80t plus 240, same denominator. Okay, and negative 20 t minus 6 t plus 2. Okay, this is what that factors to. Okay, so just go ahead and factor out the negative 20 and then do some product sum. So when I look at this, I look at the numerator for the x-intercepts, which are 6 and negative 2. And I look at the denominator for the vertical asymptotes, which are negative 8 and negative 1. Okay, so for the chart, we are going to write in the x-intercepts and the vertical asymptotes. So we start at negative infinity. The next number would be negative 8. And we get negative 2, negative 1, 6, and infinity. And for the column, okay, don't forget to put in, and this is always forgotten about, this negative 20, because this is going to negate everything in this equation, okay? T minus 6, t plus 2, t plus 8, t plus 1. Okay, and then f at x. This is okay, so number between negative infinity and negative 8, let's go negative 10. So we get negative, 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 negative. We get negative. Okay, negative 8 and negative 2, let's go negative 5. So negative, negative, positive, negative. Negative 2 to negative 1, I get negative, let's go 1.5. We get negative, positive, positive, negative. So that's actually negative still. Negative 1 to 6, I'm going to go 0. So whatever sign is on this number, like the negative 6, the positive 2, the positive 8, that's what we're taking because we're just subbing in 0. We get positive. And then 6 to infinity, let's sub in 10. Positive, 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 and we get negative. Okay, so going back up to our original question, when is this greater than 0? So it is greater than 0 here and here. So our solution set will be negative 8 to negative 2, and -1 to 6. Use algebra and a sign chart to determine the solution set for the inequality x plus 3 over x plus 1. So I'm going to write this out. X plus 3 over x plus 1 is greater than or equal to x minus 2 over x minus 3. Okay, so we just brought that term over. Okay, and just treat this entire thing as one term. Okay, so when this is greater than or equal to 0. So I'm going to go ahead and bracket all of the binomials because they are in the like fractions. And I'm going to multiply this one by x minus 3 over x minus 3, and this one by x plus 1 over x plus 1. Okay, so we get x minus 3, x plus 3, minus x minus 2, x plus 1, all over x minus 3, x plus 1. Okay, so let's go ahead and expand these brackets. This is a difference of squares, so we're going to get x squared minus 9. Minus, put this in brackets because we're going to then have to distribute this negative sign in. So I get x squared plus x minus 2x minus 2. Okay, and then rewrite the denominator. So I'm going to go ahead and distribute this negative sign into this entire bracket. I get x squared minus 9 minus x squared minus x plus 2x plus 2, all over same denominator. Okay, and then just collect like terms. So the x squared and the negative x squared cancel. We get x, and we get minus 7. And then again, same denominator. We want to know when this is greater than, or equal to 0. I forgot the equal sign. All right, so x-intercepts 7, vertical asymptotes 3, and -1. Let's do the chart. So we're going to start the chart at -infinity, -1, 3, 7, infinity. We don't need that. Okay, and we're going to put each one of these binomials down the side. I don't like how close that was. X minus 3, x plus 1. And we are going to choose numbers in the interval -infinity to -1. Let's go -10, negative, 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 and we end with a negative. Between -1 and 3, let's go 0. So just take all the signs here, negative, negative, positive, so we go positive. Okay, 5, negative, positive, positive, so we go negative. And then 10, negative, positive, 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 we go positive. So our solution set is going to be when this is greater than or equal to 0, which are the positive intervals. Because it's or equal to, we're going to use the square brackets. So we get -1 to 3 and 7 to infinity.